Imagine you're holding a drinking cup at a Roman banquet, 1700 years ago. You pour wine into it, someone lights a candle behind it, and suddenly the cup transforms, glowing blood red from the inside while still appearing jade green from the outside. Not a trick, not an illusion. The same object, two completely different colors, depending on where the light comes from. The guests around the table would have no idea why this was happening. Neither would scientists for the next 16 centuries. This is the Lycurgus cup. And what's inside its glass will force you to rethink everything you assumed about how advanced the ancient world actually was. The cup is named after the mythological king Lycurgus of Thrace, a king who made the catastrophic mistake of angering Dionysus, the god of wine. According to the myth, his punishment was to be swallowed alive by vines. That's exactly what's depicted on the cup. Lycurgus, entangled and helpless, while Dionysus, Pan, and a satyr stand around him, taunting him for his arrogance. The craftsmanship alone is extraordinary. The cup is a diatritum, a cage cup, where an outer decorative layer is carved away from the inner vessel, leaving figures that seem to float, connected to the cup by only tiny glass bridges. Most cage cups that survived antiquity have abstract geometric designs. This one has a full figurative scene. It's the only one of its kind in existence. It was first mentioned in print in 1845, then acquired, most likely, by the Rothschild family shortly afterwards. In 1950, it entered the collection of the British Museum in London, where it sits today, behind glass, admired by thousands of visitors who have no idea that what they're looking at is also one of the most significant scientific objects in human history. For most of the 20th century, scientists knew something was very strange about this cup. They could see the color change. They just couldn't explain it. Normal glass doesn't do that. The way a material interacts with light, whether it absorbs it, reflects it, or lets it pass through, is determined by its chemical composition. And there was nothing in the chemical composition of this glass that should produce two completely opposite colors from the same object. The answer didn't come until 1990. That year, researchers in England subjected tiny fragments of similar Roman glass to a transmission electron microscope, a machine that can visualize individual atoms. What they found was not supposed to be there. Dispersed throughout the glass in a perfectly even distribution were nanoparticles, specifically an alloy of gold and silver mixed in a ratio of roughly 7:3 with traces of copper. These particles were between 50 and 100 nanometers in diameter. To give you a sense of scale, a single grain of table salt is roughly 100,000 nanometers wide. These particles were 1,000th the size of that grain. They are invisible to optical microscopy. You cannot see them with any magnifying glass that existed before the 20th century. You cannot feel them. You cannot detect them with any instrument available to the Romans. And yet, they are there, precisely there, in exactly the right quantity at exactly the right size to produce the color-changing effect. When light hits the metallic nanoparticles embedded in the glass, it causes the electrons in those particles to vibrate. The frequency of that vibration, and therefore the color of light the particle absorbs or scatters, depends on the size and shape of the particle. At around 70 nanometers, gold nanoparticles absorb wavelengths of approximately 520 nanometers, which is the blue-green part of the spectrum. They let red light through and scatter green. Silver nanoparticles at a slightly different size scatter green light in a different way. The result, when you look at the cup from the front with light bouncing off it, you see the scattered green. When you look at it from behind, with light passing through it, you see the transmitted red. Same particles, same glass, completely different optical behavior based solely on the direction of light. This is the same principle that modern physicists use to design advanced optical sensors, color filters, and medical diagnostic tools. The Romans somehow were exploiting it with a drinking cup. This is where the story gets genuinely complicated, because the most likely explanation isn't that Roman glassmakers understood quantum optics. It's that they stumbled onto this effect, probably by accident, and then spent years perfecting it through trial and error, without ever knowing why it worked. Here's what we know. The particles are too evenly distributed and too precisely sized to have been added deliberately as chunks of gold and silver. Researchers believe the more plausible method was this. A much larger quantity of gold and silver was dissolved into a glass melt. Then, the artisans repeatedly diluted that melt with fresh glass, thinning it down until the metallic content reached incredibly low concentrations. At those concentrations, the metals don't stay dissolved. They naturally precipitate out of the glass as nanoparticles, clustering together in exactly the 50 to 100 nanometer range where plasmon resonance occurs. In other words, the Romans may have discovered nanotechnology the same way many great discoveries in history were made, by obsessively refining a technique whose mechanism they didn't understand, guided by nothing but the evidence of their own eyes. They knew that adding small amounts of gold and silver produced this magical color effect. They didn't need a physics degree to notice that it worked. But here's the thing that should give you pause. We have found only a handful of other Roman glasses that exhibit this same dichroic property. It was clearly not a widespread technique. It was rare, expensive, and extraordinarily difficult to reproduce consistently. Which means someone, somewhere, figured out the exact recipe, and then that knowledge was lost. 1,500 years after the cup was made, engineers at the University of Illinois decided to take its technology seriously. Professor Gang Logan Liu, a specialist in nanotechnology-based diagnostics, realized that the color-changing property of the cup was not just beautiful, it was extraordinarily sensitive. When different substances come into contact with plasmon-resonant nanoparticles, they alter the way those electrons vibrate, and that changes the color. Liu's team created a replica of the Lycurgus cup's optical structure, not at full size, but shrunk to about 1/1,000,000th of the original. Each nanocup is roughly 180 nanometers across. They arranged 1 billion of these structures on a plastic plate about the size of a postage stamp. The sensitivity was extraordinary, 100 times better than the best nanoparticle-based sensors that existed at the time. A color change not from one shade of green to another, but from green to red, visible to the naked eye. The applications they envision are striking. A device that costs under $10 and can test water quality in a developing world village. A portable blood cholesterol monitor. An early cancer detection tool that works from a smartphone. A biohazard sensor for security checkpoints. All of it made possible by studying a drinking cup that a Roman aristocrat used at dinner parties in the 4th century. The question that remains here is what we can say with confidence. The Lycurgus cup contains engineered nanoparticles. The effect they produce is real, measurable, and scientifically extraordinary. Roman artisans created a nanocomposite material, a structure in which particles at the atomic scale are precisely distributed through a host material to produce designed optical properties. By any reasonable definition, that is nanotechnology. What we cannot say is whether they knew what they were doing at the atomic level. Almost certainly they didn't, not in the way we understand it. But does that matter? The engineering was real, the precision was real, the result was real, and there's a detail that researchers keep circling back to. The cup is the only fully intact ancient glassware with these optical properties. But it's not the only Roman glass that shows dichroism. There are fragments, shards from other vessels that exhibit the same behavior, which means this wasn't a one-time accident. It was a technique, a reproducible intentional technique, controlled well enough that multiple objects were made with it. Someone in the Roman Empire knew how to make nanoparticle-embedded glass. Not theoretically, practically. With their hands in a workshop without instruments, without a periodic table, without any framework that would let them understand what they were building. And then that knowledge disappeared so completely that it took modern electron microscopes, quantum physics, and 20th century materials science to figure out what they had done. The Lycurgus cup sits in a case at the British Museum. If you visit it without knowing this story, it looks like a beautiful old drinking cup. With this story, it looks like something else entirely. Evidence that the gap between ancient capability and modern understanding is far narrower and far stranger than the history books suggest. The technology was there. The cup proves it. The only mystery left is, what else did they know that we've forgotten?